Okay, so today we're going to be talking about absolute values and the real number line. So we're going to begin with the following definition. So 2.2.1 definition. And this definition is just the definition of the absolute value. So the absolute value of the real number A is defined as a piecewise function. So it's going to be A if A is greater than 0, 0 if A is equal to 0, and then finally negative A if A is less than 0. So this is the formal definition of the absolute value. You're probably used to just thinking about it as taking the positive of the number that you put in, but formally it's defined as this piecewise function. And of course, we can have examples like absolute value of 2 is just 2, absolute value of negative 1.3 is just 1.3. And if you plug these values into this function, you'll see that this is what they evaluate to. So, for example, if A were to be negative 1.3 of all these conditions, this is 0 there. Negative 1.3 is less than 0, so we would take negative of that number. So really, I should write, I'm using the formal definition, negative of negative 1.3, which is going to be just 1.3. Okay. Now, on the real number line, you can think of the absolute value of A as the distance from that number A to 0. So, for example, just draw our standard real number line, and here's 0. Then, if we pick A to be anywhere on here, so for example, negative 1.3, then how far away is negative 1.3 from 0? Well, it's precisely 1.3 units away from 0. So you can think of the absolute value of A, or interpret it as the distance from A to 0. That's the geometric interpretation of this absolute value function on a single scalar A. Okay. So another term that I might use sometimes by accident is so it's a distance. But another way of thinking this is like a metric. And in upper level courses, especially in grad school, if you go to grad school, metrics are very important. And distance, the absolute value in this case, is just one way of defining a metric. So that's just something for the back of your mind, I suppose. All right, so now that we have this definition, we have the geometric interpretation of it, we know how it works, we need to prove, or at least like state properties of this definition in the form of a theorem. So this is theorem 2.2.2. Theorem, and this is a 4-part theorem, and it says that for part A, we have that the absolute value of A times B is equal to the absolute value of A times the absolute value of B. For part C, we have the absolute value of A squared is equal to A squared. Oh no, it's part B, I'm sorry. For part C, we have that If C is a number greater than or equal to 0, then the absolute value of A is at most C if and only if, by conditional statement, if and only if negative C is less than or equal to A, which is less than or equal to C. Okay. And then finally, part D, we have that negative absolute value of A is less than or equal to A, which is less than or equal to the absolute value of A. Now, this is the statement of the theorem. We're going to be recalling Theorem 2.2.2, part C, at least twice with some following arguments. So make sure that you have that written down next in your notes so that you can recall it when I say it out loud. So technically, we would have to prove all these things, but the proofs are really just case-by-case analysis of the definition and the statement in question. So for example, if we wanted to look at maybe the proof of part A, we have several different combinations of values that A and B can have. They can both be positive, one can be negative, they can both be negative, right? So for example, so we can say like, let's just like kind of walk through the beginning of the proof of part A. So let A and B just be any arbitrary real numbers. And then we have cases. So case 1, A is greater than 0, and B is greater than 0. Okay. So in this case here, observe that, so then say maybe the absolute value of A is equal to A by the definition, right? If you're greater than 0, it's just the same value. And the absolute value of B is equal to B. Okay. So absolute value of A times the absolute value of B is just equal to A times B, right? Which is going to be equal to the absolute value of A times B, since A times B is going to be greater than 0 in this case. So this equation here establishes part A when they're both positive. So then you would have to consider the negative maybe. So maybe I'll go ahead and walk through them. I don't think the textbook actually gives the full proof, so I'll walk through it. So in case 2, we can suppose that they're both negative. So A is less than 0, and B is less than 0. So we're in this case here for the definition of the absolute value, so we can say then absolute value of A is equal to negative A, and the absolute value of B is equal to negative B. So the absolute value of A times the absolute value of B is equal to negative A times negative B, which is equal to AB. Okay. I wrote that down, right? So now we need to figure out So what's the absolute value of A times B? Well, this is actually equal to, we just stated the absolute value of A times B, since A times B is positive. And a negative times a negative is positive, so the inside will be positive, so we just write that instead. So that case 2 establishes that equality there. So what are the other cases? Do you want to speak up? Can one of you tell me what are the other cases I need to consider? Okay, so far, the cases are they're both positive, and then we have they're both negative. So what are the other possible combinations we could have?
One positive, one negative, and then 1 0.
Right, at least 1 0 and at least 1 negative. Right, and that's exactly what you said in ways. So maybe case 3, we can say, we can just assume without loss of generality, which I don't think I've said that before. Without loss of generality, we can just assume that A is 0 and we don't care what B is. And one way of interpreting what that means is that we can prove it for A is equal to 0, which is equivalent to proving it if B is equal to 0. So if I ever write this, W log like that, I mean, without loss of generality, we'll say that A is equal to 0. The same argument that I'm going to give will also hold if B is equal to 0. So then, I can just say that the absolute value of A times the absolute value of B. So if A is equal to 0, the absolute value is 0. So it's 0 times the absolute value of B, which is equal to 0. And this is going to be equal to the absolute value of A times B, since A times B is equal to 0. Right, if A is 0, then the product of those two real numbers is going to be 0. And then case 4, we can have, again, without loss of generality, we can say like A is less than 0 and B is greater than 0. And again, when I say without loss of generality, I mean that if we prove for A less than 0 and B greater than 0, that's the same thing as proving if B less than 0, A greater than 0. So then absolute value of A times the absolute value of B is equal to, say, negative A times B. Okay. And this is going to be equal to, so the inside, so if A is negative and B is positive, then the product is less than 0. So this is equal to negative of A times B, which is equal to the absolute value of A times B, since A times B is less than 0. And that exhausts all the cases, QED. That proves part A. I know it seems tedious, but when you're proving mathematics from the ground up, you have to prove every statement that you come across. So a similar type proof for part A will also apply for part B. In fact, yeah, it's very similar. So part B, I'll leave as an exercise. You should definitely this is an exercise. And then let's say part C is given in the textbook, and part D is a immediate consequence of part C. So read the proof of part C, write it down, and then you can use it. But we're going to use this theorem in a few proofs moving forward. So keep that in mind. So I would like it if you talked a little bit more. I don't want to get into the habit of just talking at the computer screen. I'd like to hear back stuff sometimes. Okay. So what is next? Oh, one of the most important inequalities of this course, and one of the most useful inequalities in general. So this is 2.2.3, and this is called the triangle inequality. Again, one of the most useful things to know in proofs and analysis and all sorts of other mathematics courses. So what does it say? It says that if A and B are real numbers, then the absolute value of the sum, so the absolute value of the sum is at most the sum of the absolute values. Okay, so let's look at a proof of this. So in order to prove this, we're going to observe part C from this theorem. So in particular, we have that, what do we have here? We have that, oh, we also need this as well at some point. All right, so just notice first, so we're going to use part D and then use part C. Notice first that if you have a scalar, then it's bounded above and below by absolute values, negative on the below, positive on the above. So we can say something like by 2.2.2 part D, first observe that we have negative absolute value A is at most A, which is at most the absolute value of A, and negative absolute value B is at most B, which is at most the absolute value of B. Okay. Now let's add these inequalities together. So if we add the left-hand side, we get minus of this sum. So if we add that and that, that's like in the lower hand of this inequality. And then in the middle, we have A plus B. And then on the right-hand side, we have absolute value of A plus absolute value of B. Okay. Now, if we look to part C here, we have that absolute value of A is at most C if and only if this inequality holds. Well, look what we have here. We can think of this quantity here, we can think of that as C, right? Like this quantity right here, we can think of that as C. So this value is bounded above by C and below by negative C. Which means, since this is a biconditional statement, if that holds, then we have that this quantity in absolute value is bounded above by that value C. So this quantity right here in absolute value is bounded above by a quantity C. So then we can say, then by 2.2.2 part C, we have the absolute value of A plus B is at most, so that's that part right there, the quantity C, which is just the sum of the absolute values. And that's it. Okay. And I think in your textbook, it's left as an exercise. I think the second problem from this section is to establish when equality holds. So as an exercise, when does equality hold? So when does the absolute value of A plus B equal the absolute value of A plus the absolute value of B? Okay. Now, we actually should probably generalize this inequality to deal with in terms, in scalars, in real numbers, not just two of them like we did here. So let's go ahead and do that. So I'll call this the general triangle inequality. Okay. And what does this state? It states that if A1, comma, dot, 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 A n, if those are all real numbers, then the sum, so the absolute value of the sum of these numbers is bounded above by the sum of the absolute values. So then okay. So you can see that the triangle inequality is a special case of the generalized triangle inequality when you take it into B2. Okay. So how would this look? I don't know, let's see. I think the best way to move forward on the proof of this is by induction. So because if we look at this statement here, this statement satisfies a base case for induction on the number of real numbers that we're considering. So know this. Uh, 2.2.3 that satisfies or satisfy a base case. For induction on N. Okay. So now we need to make our inductive hypothesis. So then we can say for our inductive hypothesis, we can assume the statement is true for all k greater than or equal to 2. So assume that I'm running out of room, but just I'll write right here. Use that word. So assume A1 plus dot 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 plus AK is at most this sum. So AK there for all k greater than or equal to 2. And now we want to show that that sum also holds for k plus 1. That's the inductive step, right? So, how can we do this? We can say, so, we next consider, we need to erase over here. So we're going to consider a sum of k plus 1 elements. Okay. So let's go ahead and look at what that sum is. So we have A1 plus dot 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 plus AK plus AK plus 1. Okay. Now, what we do know by our inductive hypothesis is that we can say this value right here, that's a single scalar, that's a single real number, right? That sum is a single real number. So we can say that this inequality is at most this inequality by our inductive hypothesis, right? If that's just a single number, that sum, we know that the sum of this number and that number in absolute value is at most the absolute value of the first number, plus the absolute value of the second number. So that inequality that we wrote is based off of our inductive hypothesis. Since we know that we can do that for all k greater than equal to 2, that's 2, so we can do that. But then this is a sum up to k, which k is greater than equal to 2, and we know that this sum is going to hold by our inductive hypothesis again. So then this sum is at most the sum of the absolute values. And we're done. So that completes the proof of the general triangle inequality. And again, I didn't write it out, I didn't have the room, but from here to here was our inductive hypothesis, since we can do that with two numbers. And then from here to here, we use the inductive hypothesis again to get an inequality on that value there. Now, I know that many of you have not made it into courses yet that involve estimations. Most of the courses you've had involve equalities, not inequalities. But as mathematics gets more complex, depending on what area you go into, more than likely you will be looking at inequalities instead of equalities when dealing with theorems and ideas. And the whole point is that a lot of times equalities are just too complicated to exist, so you need an inequality to do your best to give an estimate. So just know that we are using inequalities going forward as estimates on quantities. Okay. So that's the first, I guess, like corollary to this simple triangle inequality here, because it was just a simple application of induction. So let's look at a few other corollaries of this main triangle inequality. Okay, so let's look at 2.2.4, and it's the corollary to this theorem. Okay, and it says first that the absolute value of A minus B, all in absolute value, is bounded above by the absolute value A minus the absolute value B. I'm sorry, I needed something off there. There we go. The absolute value difference. So that's a lower bound on the difference. And then for part B, we have that the absolute value of A minus B is at most the sum of the absolute values. And so these are immediate consequences of this theorem here, and I can show you why the proof. So let's look at proof of part A. So what we can say is that, so we want to prove this inequality here. So one thing I'm going to notice is that, the absolute value of A is equal to the absolute value of A minus B plus B, right? I just like added a zero basically, right? But then by the triangle inequality, this is at most the absolute value of A minus B plus the absolute value of B. So triangle inequality implies that the absolute value of the sum is at most the sum of these absolute values. So then if we subtract B on both sides, so maybe this is a comma, so which implies that say absolute value A minus absolute value B is at most the absolute value of A minus B. Right? So that wasn't too hard to discover. So in a similar fashion, but also maybe, we have absolute value of B, which is equal to the absolute value of B minus A plus A, which is at most, by the triangle inequality, the absolute value of B minus A plus the absolute value of A. Okay. So if we subtract A on both sides, is that what I want to do? No. I'm going to subtract the absolute value of B minus A on both sides and subtract B on both sides. Or absolute value of B. So let's see. So which implies so negative of the absolute value of B minus A is at most the absolute value of A minus the absolute value of B. So the important thing to note here is this and this. So I see that from above, this quantity is bounded above by this here, and then by below, it's bounded by that quantity times a negative. So by 2.21c or something, what do they call it? That theorem I had of 2.212 part C. So we can say by 2.2.2 part C, this implies that the absolute value of this is bounded above by this quantity. So this is that is at most that quantity there. So then we establish part A. Okay. And next, we should prove part B. Okay, so here's the proof of B. So it's a similar trick. We're going to do this like adding zero trick in the original triangle inequality. So I think it's something like, I noticed that, so what can we say? Maybe, oh, it's easy, we're talking about, so A plus, right now, A minus B, the absolute value, is equal to A plus minus B. Same thing, right? Which by the triangle inequality is at most that. But this is the same thing as the absolute value of B. And then we're done. And that proves part B. Okay. So we have these like very theoretical type proofs, but we also need to remember that there is a geometric interpretation or a picture that you can always draw with most things in analysis. For example, let's consider the following question. So suppose we want to know something like, I don't know, we want to know when this inequality is at most x plus 1. Okay. Now, before using any of the properties of absolute values that we've derived and proved, it is useful to draw the thing, draw what's going on here, and just look at it for a moment before you start acting. So I'll try my best to draw this picture well. So first, I'm going to draw this function, this linear function x plus 1. So when x is, well, first I need to draw my ticks here. Okay, so let's focus on this first. So when x is 0 here, let's take one right there. So this function looks like this is x plus 1, where y is equal to x plus 1. That line there. So then this is the absolute value. So what does that look like? Here is okay, so when x is equal to 0, we just have absolute value of -1, which is +1. So right there. When x is 1, we have 2 minus 1, right? Which is, hold on, yeah. There, hold on, let me make sure. X is 1, 2 minus 1 is 1, so it's 1. And X is, well, let me make sure. X is 0, 2 times 0 is 0, minus 1, absolute value goes up. When X is 2, we have 4 minus 1 is 3. 1, 2, 3. The magic right there. When X is a half, this is 0. That's why it looks like that. Okay. X is a half, so there, so that's y is equal to 2x minus 1. That's actually a pretty good drawing. That's pretty symmetrical. Okay. So just looking at the picture, what values of x satisfy that inequality? Just by looking at the picture. Anybody? Hey, when is, go for it. What are you about to say?
When x equals 0 and 2?
So not when equals, when x is in that interval. Okay. So if x is in that interval, notice that the graph of this function lies below the graph of this function. Right? So that's a perfect example of where drawing a picture can give you a heads up before you start doing anything. Okay. So I'll leave it as an exercise for you to derive this correct solution using the properties. So yeah, find the correct solution for x for that inequality and verify that it matches up with that picture. Okay, so what do I have next? Oh, a few more definitions and then we'll be finished for the day. Okay.
Excuse me, sir, I have a question. Now, for this question, the answer is that interval between 0 and 2,
Yeah, good.
including 0 and 2.
Yes, including less than or equal.
Oh, yeah.
Okay. So when considering these real number lines and these drawings, as I mentioned at the beginning of class, the absolute value can be thought of as the distance from that scalar to 0, distance, right? So in particular, or more generally, the absolute value of a minus b is the distance between a and b. So that's the more general idea that I mentioned at the beginning of class. Okay, so keep that in mind. Whenever you see absolute values of the difference, think distance between those two numbers. And never forget that, especially in this course. Okay, so now we have a definition. 2.2.7 definition. So we're going to say that A be some arbitrary real number and epsilon be a positive real number. So then the epsilon neighborhood okay, of A is the set denoted by capital V sub epsilon of A. And it's the set of all real numbers x such that the distance from x to A is less than epsilon. So epsilon neighborhood, another way of some other terminology of this, which I sometimes might say by accident, sometimes also this is the definition, but sometimes I'll say an epsilon ball. This is like a general name for this specific definition on the real number. An epsilon ball, epsilon neighborhood, they mean the same thing to me. Okay, so this leads me to with this definition. Well, actually, we should probably interpret what this looks like first before proving anything. So we have the real number one, and then for any given number A, you can pick an epsilon. So first you pick epsilon, and then once you pick your epsilon, you get a epsilon ball around A, or epsilon neighborhood around A. By just A plus epsilon going that way, and then A minus epsilon going this way. So anything in this interval will be in the epsilon neighborhood around A. Okay, so this is a rather simple theorem. 2.2.8 theorem. So we're going to say let A be some real number. So if x is in the epsilon neighborhood of A for all epsilon greater than 0, then x is equal to A. All right, so why would this be the case? Well, okay. This is actually a corollary to a result we had on absolute values that we proved in the previous lecture. But let's just see if we can argue why it's true, only based off of this definition. So, maybe suppose to the contrary, that x is an element of the epsilon neighborhood of A for all epsilon greater than 0, and not that, and x is not equal to A. Okay. So, so if x is not equal to a, then there is some distance between x and a, right? If they don't equal each other, then there's a midpoint between them, right? There's some midpoint between them. So, like, oh, we can use this picture. All right. Like, suppose that it doesn't equal to a. I need to practice what I preach. This picture makes it so much easier to think about other than just trying to piece together the logic. There's x, there's a, there's some epsilon neighborhood, right? X doesn't equal a, right? Which means that there's some like point in between them, right? So we can just say that point is going to be equal to x plus a over 2. The midpoint, I don't know, that'll work. Pick the midpoint. And then once we have that midpoint, we know that this point P right here doesn't equal a, so there's some distance between them. So then what we could do is say, we can say let's epsilon naught equal the absolute value of P minus a, which is equivalent to this distance here. So then that right there is going to be a plus epsilon naught, and then over here, that'll be a minus epsilon naught. And now x is not contained in that epsilon neighborhood, which is a contradiction since it's supposed to be contained in every epsilon neighborhood. So maybe that's like overkill, but that's the first thing that I thought of when I saw that picture. So then we say, next, let P equal to the midpoint between x and a. And epsilon naught equal to the distance from P to A. Again, thinking in terms of distance is really helpful when you draw these real number lines. It helps you see like, oh, if they don't equal, then there's distance. Put something in the middle, there's still distance. That new distance from A, we're going to call that epsilon. And now we can make a new ball around A that doesn't contain X. So then, we can say that the distance from X to A is greater than epsilon naught, which implies X is not contained in that epsilon naught neighborhood around a contradiction, since it should be for every epsilon. I think that's a decent proof. It's true. Okay. So since that's the midpoint between X and A, we know that, yeah, it's the picture says it all. Okay. Okay. So a few more things to note. Yeah, I'll do it right here. I don't want to erase that picture yet. So. So let's consider two sets. We'll say that U is equal to the set of all x, such that 0 is strictly less than x, which is strictly less than 1. And we'll say that I is the set of all x, such that 0 is less than or equal to x, which is less than or equal to 1. Okay. So with these definitions, I just want to observe a few things before we enter this class. So if we drew this guy, right? So every real number in that interval belongs to the set U. If we pick any number in that interval, there's going to be an epsilon ball or epsilon neighborhood around that number. It's completely contained in this set U. So for example, if I pick this number right there, that could be like an 8 or something. Then obviously there's distance between an 8 and 0. So I can put a little epsilon neighborhood around an 8 and it's completely contained in U. In fact, this holds for any number that you pick inside of U. And if you recall, there is no smallest positive real number. So no matter how close I get to 0, there's no smallest number in U. So no matter how close I get to 0, there's still some distance between here and 0. So I can pick a small enough epsilon and squeeze inside there a little epsilon ball around that point, no matter how close I get. So every point in here belongs to some epsilon neighborhood that's completely contained in that interval. What about I? Well, now it's the closed interval. So here, everything not including 0 and 1, everything in there, we can still do the same. We can still squeeze in epsilon neighborhoods no matter like, what we pick, as long as it's not 0 or 1. However, if we pick, for example, 0, no epsilon ball around epsilon neighborhood around 0 will be completely contained in this set I. For example, if I just take epsilon maybe this far out, that's like epsilon, the epsilon neighborhood is defined as that interval, right, to the left and right. This would be like minus epsilon. So notice all of this business over here is not inside of I. No matter how small I try to make epsilon be, it's always going to poke out a little bit. So it belongs to the set, and every epsilon neighborhood around that point sticks out of the set in question. And we'll learn that these have very special names. I forget what this book uses for terminology, but it's either an accumulation point or a limit point. But if every neighborhood intersects the set and doesn't, then it's a very special property to have for a given set of real numbers. Same thing with 1. No matter how hard we pick to find an epsilon neighborhood around 1, it's always going to stick out a little bit. It's like 1 plus epsilon right there. And it's like 1 minus epsilon right here. And you see that it sticks out over there. Okay. So just some interesting things to note about these epsilon neighborhoods and why we want to even define such a thing. And the reason is, one of the reasons is that it tells us about special points in a set of real numbers. Like these are special. There's values 0, 1. Okay. So let me stop the recording now.